Dear A-level students, as you are aware, this is COVID time, and we have gone IT in interest of adding on knowledge. So this lesson is actually applied mathematics for advanced level, paper 425/2. Our topic for this lesson, our major topic, is probability distributions. That's our major topic, probability distributions. Now, probability distributions, those ones who are aware where we began from, is a new topic because we want to make a difference between what we did previously and what we are doing during this time. So anything not covered on the other subtopics will be covered during the physical interaction. So we won't begin this as our new topic, probability distributions, and we hope you have logged in or you log in at a later time. Be aware that you also need to be making notes, understand carefully so that we don't repeat these things. So for you to understand probability distributions very well in applied mathematics, you need to understand these basic definitions. The basic definitions. When you understand these basic definitions, then you will have no big problem with the probability distributions. One, you need to understand what we call a variable. What we call a variable. So what's a variable? That's the beginning point of probability distributions. A variable, by definition, is a quantity. A quantity. It's a quantity. A variable, by definition, is a quantity. It's a quantity that changes. Now, if it's a quantity that changes, then we can have a number of examples of a variable. For example, the number of COVID patients, COVID-19 patients who die. And you see, this quantity, this number keeps on changing. A quantity which changes, number of COVID-19 patients who die. So it's a quantity. Last time we were talking about 20 people, now we're talking about 50 per day. That quantity is keeping on changing. That's one. A quantity which keeps on changing is a variable. We can talk about our weights. Our weights. Weights of students. Weights of students and teachers, for example. Now when you talk about weights of students and teachers, the weights of students will be changing, varying by type of student, his background, food eaten, by genetic nature. We can also talk about the teachers having different weights. There are short teachers, there are tall teachers, there are compact teachers. So they have various weights. Our marks keep on changing. So because these marks keep on changing, people will get 90, people will get 40. So they become variables. A variable is something which changes. Another concept which we must note, I hope you can see up to that level, is now what we call a random variable. Why do we call something a random variable? A random variable. Now, so, a random variable. Now here, I've added here, a random variable. We have said here is a quantity that changes. So a random variable is a variable is a variable whose whole value is a numerical outcome of a random phenomena. Now here I need to explain this. It's a variable whose outcome is a numerical value of a random phenomena. Now because it's a numerical outcome and it's a random phenomena, that means it has got a given probability, a chance of occurrence. Has got a chance of occurrence. A chance of what? Occurrence. You need to understand this carefully. Something which is having a random phenomenon has got a given chance of occurrence. Like we talked about the COVID patients. There's a chance that you will die when you get COVID. There's a probability you will die. There's a probability you get COVID when you don't wear a mask and you expose yourself to the COVID environment. There's a probability that you will not get it when you go to a place where people don't have COVID. So there is a chance of occurrence, a likelihood of occurrence. So it's a random phenomena. It's a random phenomena. Once you have understood that it's a random phenomena, that means there's a chance of occurrence. You need to understand that these random variables, we represent them with a capital letter. It is those whole values, we represent them with the capital letters. We can say X, a capital letter, say X. To represent, like when we are talking about the number of people who are having COVID, we can call it X. The number of people who are infected in a given school, we can call it X. If this is GBSS, we can call it X1. A number of people who are infected in another school, we can call it X2. A number of people infected, we can call it X3 in another school like that. So this one becomes a distribution of a random variable, number of people who are infected by COVID-19. Once you have understood that, then now, because they have a random phenomena, that means what? They have given probabilities. And when they have given probabilities, the implication therefore, they have what we call a probability distribution. So, a probability distribution then is these respective outcomes. The third one now, a probability distribution. Now, a probability distribution basically now becomes the outcomes and their respective probabilities. If we have an outcome with a respective probability, we call it a probability distribution. If the outcome is to get COVID and you die is X1, and to get COVID and you survive is X2, and the probability of death with the COVID is 3/4 when you have it and you are healthy, that means the probability of death will be 1/4. So this one forms what we call a probability distribution. A probability distribution, because you'll have two outcomes here. This one, we have called it an outcome of having COVID and you die. Then outcome of having COVID and you survive. And this is now death. So this is now called a probability distribution. So we can have a probability of X is equal to X, where this respective outcome means that you will die when you have COVID. This one means that you will survive when you have COVID. So our outcome here is death. Then the one is the complement, which we did in probability theory, or which you have done in probability theory. So after knowing that, it is also important for you to understand another word, which we call the types of probability distributions. Before I go, you need to understand these basic types of probability distributions. Now, for this class, for A-level students, you only need to understand that there are two types of probability distributions. One type, discrete probability distribution. A discrete probability distribution. That's the first type. A discrete probability distribution. That's the one type. And what are these? Or what's this probability distribution? This probability distribution is the one which takes on whole numbers. Whole numbers. Whole numbers. Whole numbers. Like 0, 1, 2, 3 onwards. You can also take on only counting numbers from our field of mathematics, basic mathematics. 0 is the first whole number. These ones are counting numbers. That's one. It takes on whole numbers without decimals. Or it can take only negative integers like -1, -2, -3, but also without decimals. Without decimals. Any random variable which takes on values which are either whole numbers, counting numbers, or integers without having decimals is called a discrete probability distribution. It's called a discrete probability distribution because it's taking only whole numbers. Any random variable that takes on whole numbers is called a discrete probability distribution or a discrete random variable. After knowing that, we move to the next one, the next type, which we call a continuous random variable. A continuous random variable. Now, the difference that a continuous random variable, it takes on values in a given range. Say, we can say from 40 less or equal to x less or equal to, take for example 100. It takes on values in this range, including decimals in that range. Including decimals in this range, e.g. our weights. Our weights can be, the last time you measured your weight, you never know, could be 68 kilograms. Then you add and you become 68 after having a lockdown and eating a lot of food. You now have 68.5 kilograms. Then you continue overeating, then you end up by getting 70 kilograms. Or you get 70.2 kilograms. You see? So this one is a continuous random variable. But there are also people who may be having, could be 50 kilograms or 55.1 kilogram. So it is varying in a given range, including decimals in that range. Such a distribution is called a continuous random variable. So after you have known that, then it is also important for me to introduce you one other word before we go into one bit of those random variables in detail. It's important for you also to understand a word called a probability density function. I will be explaining them also in detail as we handle them one by one. Now, a probability density function. These are words which keep on disorganizing students. A probability density function. Now, by definition, a probability density function, which we normally put in short, PDF in short. A probability density function is a function which allocates probabilities. Is a function which allocates probabilities. Now that means what? You have given observations like x1, x2, x up to xn with their respective probabilities. So if this function can allocate these values, their respective probabilities, probability of x1, probability of x2, if this x1 and this x2 onwards like this, probability of xn onwards, then it's called a PDF, which we shall see within this very lesson. I'm going to give an example of a probability density function. So those are the keywords, first of which you need to master for applied mathematics. One, you need to know a variable, something which changes. A random variable has got a phenomena with a given probability. A probability distribution is just an outlay. That outlay, given values with their respective probabilities. Then a probability density function, a function which will allocate its probabilities. Now let's go into detail and begin looking at now let's get into detail and look at what we call discrete probability distributions. Discrete probability distributions. I've already said that for discrete probability distribution they take on whole numbers. So I'm going to now begin giving examples of discrete probability distributions. Now, the immediate example which comes from our basic knowledge, EG1, is given this observation. If you remember our senior 2 O-level studies, very well, given observations. If we have observations, like 1, 1, 1, 1, 2, 2, 3, 3. If we have those observations, in our senior 2 for O-level mathematics, we'll do some basic placing this in a table. I would form this a frequency table. We would form a frequency table of this. Now, we can form a probability distribution out of these occurrences. First, this one I've taken random nature. I've given them random outcomes. Why? I will just mention them randomly. And I made this one 4. Randomly, I made this 2. Randomly, I made this one also 2. There are 3. These ones are 2. These ones also are 2. But these ones are 4 by random. So randomly, I've selected these figures. Now, if I've selected these numbers randomly, I've just made them from my head. So it's a random phenomena. The phenomena is random because I manufactured them from my head. I just created 1, 1, 1, 1. I've also created 2, 2, 2. So it's a random phenomena. So it becomes a random variable of what? Of counting numbers. So because it's a random variable of counting what? Numbers. The question then would be, from our probability theory, what's the probability? What's the probability that I get an observation which is equal to 1? I would write it like this. Where my x is a random variable, the outcome from observations 1, 1, 1, 2, 2, 3, 3. The outcome from these observations, which have been manufactured by me, who's telling you these concepts. Now the outcome of this, I'm not calling that to be a random variable. These outcomes here. So if these outcomes are random variable, the question then is, what's the probability I will get an observation which is 1? I will get an observation which is 2. I will get an observation which is 3. So the probability x is equal to x. Because we do not do this using a capital letter. All random variables, we normally denote them using capital letters. So I have chosen this one, x, as a random variable of my outcomes, which I have selected there. So I'm now calling this x1 as the probability of getting the first observation. My first observation is probability of x is equal to a 1. This possibility of getting a 1. Now the possibility of getting 1 shall be equal to the number of those 1s over the number of elements in a sample space from our probability theory. Certainly, we have been talking about this over and over. You need to have ideas of probability theory. Those are basic ideas in your first term in HSC. So the number of those ones and the number of elements in the sample space. So how many ones are here? It's 1, 2, 3, 4. So there are 4 ones. How many observations are here in this sample space? 1, 2, 3, 4, 5, 6, 7, 8. So this is 4 out of 8. Now, the probability that I get an observation, the second observation, according to the observation, is, the second observation is 2. What's that chance? So it will be the number of those 2's over the number of elements in the sample space. How many are there? So these ones are 2. 2 out of 8. Now, similarly, the possibility of getting the third observation, which is equal to the probability of getting the 3, shall be equal to the number of those 3's over the number of elements in the sample space, which is also equal to 2 out of 8. So, this is what we call a probability distribution. The probability distribution of these random numbers, which I manufactured from my head. I manufactured these numbers using a random phenomena by just writing them randomly. When you write them randomly, and you get their respective probabilities. So if a phenomena is random, and you get their respective probabilities, then you form what we call a probability distribution. But this probability distribution, normally we write it in a table format. We don't just leave it hanging like this. So we write it in the form of a table. So, now that you have been following, and I hope you're following carefully, we can say the probability distribution. The probability distribution. The probability distribution of the numbers generated of 1, 2, and 3. So we can write them like that and say our x, then our x values, we have our x values are 1, we had a 2, and we had what? A 3, and we had their respective probabilities. We write like that. A capital X is being equal to a smaller x. There's no mistake here. This is a capital X and this is a small x, and its respective probability. The probability of getting a 1, we have it here, is 4 out of 8. The probability of getting a 2 here is 2 out of 8. The probability of getting a 3 here is also 2 out of 8. So, after understanding this, if you have understood this, then there is something which you must note as a student of applied math. What do you do, what do you get after summing these respective probabilities? That's one key issue which you must have in your mind as a student of applied math. The key issue is that when I sum, which you must have in your mind, and keep it until when you finish your final examinations. The key issue is that the sum of all x, where x is a random variable which I've already defined, probability of x which is equal to x, that means discrete exact value, like here, these are whole numbers. These are whole numbers. For this case, there are the first 3 counting numbers, 1, 2, and 3. So they are whole numbers, they are counting numbers. There's no 0 here, so I can call them counting numbers. I can also call them natural numbers. So the sum of all x, all the values for their respective probability should be equal to 1. That's a key issue as a student of applied math. When you sum all the probabilities of all these observations, you should always get 1. And goes back to our concepts of probability theory, that all probabilities, we remember when we did probability theory, we said the probability of any element is less or equal to 1. Must be lying between 0 and 1. This from our probability theory. Now, when you sum all the probabilities, if item is not having probability 0 and you have probabilities in that range, the maximum value should be 1. That's the key issue you must have in your mind. So, having looked at that as our first example, we would like also to look at a sketch. Now, remember that for principal maths, we need to be having ideas of sketching, curve sketching. In pure maths, even in applied maths, we need to have these ideas of curve sketch. So we want to look at a sketch of what? A probability distribution. A sketch of a probability distribution. Now, just from our example, given our x values, remember our the x values which we have just had 1, we had 2 and 3, and we had the respective probability of x being equal to x. This one was 4 out of 8, and 4 out of 8 is equal to 0.5. Then we had this one as a 2 out of 8, and which is equal to 0.25. This one is a quarter. Then this one gave us also 2 out of 8, which is equal to 0.25. If somebody has told you sketch the probability distribution. If somebody has told you to sketch this probability distribution, what you must be aware, for this particular sketch, you will have the probabilities on the y-axis and observations on the x-axis. So we shall plot these observations on the x-axis and these respective probabilities on the y-axis, and that will be the sketch of the probability distribution. So for this particular case, when they say make a sketch, does not necessarily mean that you should have a graph, but you should have general knowledge and logic. You cannot plot. Well, let me plot this, then you see, and I will explain. For the ones which I have just done here, I'm going to plot this by a free sketch. I'm going to plot my 1, my 2, my 3 with their respective probabilities 0.5, 0.25, 0.25. That's what I'm going to plot. These ones are going to take on the x values, these ones are going to take on the y values, the y-axis. These are going to be in the x-axis in short, and these are going to be in the y-axis. Now, so when you're making a sketch, what I'm trying to say is, 1, you should have some basic knowledge about plotting. 1, the issue of a scale. Have that rough idea about a scale. All sketches must have some basic idea about a scale. That's 1. Then also have some basic common sense. For example, if I'm plotting 0.5 and 0.25, which one's bigger? Those are basic ideas. So a sketch, when they say a sketch, does not necessarily mean that you should just plot anything randomly. You should have some basic common sense showing. So our sketch of our PDF will be having this. This is a basic example. And in study device, we'll use a ruler. Much as you're using it. You may not measure, but use a ruler. So, now, more observations are going to be here. So more observations are going to be on the x-axis. There's no need of you again labeling here and say x-axis, just observations. So my first observation is 1. Are you seeing? Another observation. So you see this by just common sense. When I observe this, the next one is 2. Have some idea that this should be having similar distance away. So after having this, then the probabilities now, since I have the probability 0.5 as the smallest, I can begin 0.5, then I keep on adding on. I can even say 0.1, 0.2, 0.3, 0.4, 0.5. So if I have that, I'll have here 0.1. I have 0.2. I have 0.3. I have 0.4, 0.5. And here, you need to label the probability of x is equal to x. These are the respective probabilities. Of course, we know that this is the x-axis. Ideally, this is the y-axis. Now, even if you have not labeled, but you have put here observations and here the probabilities, this is a sketch of our PDF. Now, this one here is having a probability of 0.25. So when you are drawing, there must be vertical lines. You raise this a vertical line. You see, by common sense, 0.2 and 0.3. So 0.25 is between 0.2 and 0.3. So you must raise a vertical line like this. You must raise a vertical line in between that. That's the common sense I'm talking about as an advanced level student. You don't begin just making things haphazardly and say, since 0.25 I can just put, so 0.25 is between 0.2 and 0.3. So this will be 0.25. Then the probability of 1 is 0.5, sorry, you should raise it up to that. That's the probability of that one. Then the probability of 2 is the one which is 0.25. So you raise it up to that point. Then the probability of 3 is also 0.25. Raise it up to that. So they have vertical lines like that. That's the common sense I'm talking about. This one here, probability of 1 is 0.5. So you raise it up to 0.5. The vertical lines. Then the probability of 2, 0.25. 0.25, so you raise it there. The probability of 3 is that one, so you raise it up there, like that. So this one is a sketch of our PDF, of our random numbers, 1, 2, 3. That's our sketch. So after understanding that, so keep this in your mind. 1, sketches of this nature. Observations will be on this side and their respective probabilities will be there. After getting that, we can also look at the second example of a discrete probability distribution. The second example of a discrete probability distribution. I can give a die, the issue of a die. Now, we are very familiar with our die right from our O level. The sample space of a die, and from our beginning topics, the sample space of a die is 1, 2, 3, 4, 5, and 6. That's our sample space of a die. A sample space of a die is from 1 up to 6. From our O level, we said a die is 6-sided. 6-sided and it's uniform. We described it, but I can repeat. Now, if this side is numbered 1, this side is numbered 2, this side is numbered 3, this side is numbered 4, this side is numbered 5, and this side is numbered 6. Then you put this in a box, then you toss it. We give example of Ludo. Those people who play Ludo will get have that, and all the sides are uniform. So you'll have one side is having one hole, the other side is having 2 holes, the other side is having 3 holes, this one is having 4 holes. So if you toss that die, if you toss this, the likelihood you'll get either one side having 6 holes, one side having could be 1, one side having 2, one side having 3. So they are equally likely. So our random variable for this case, we can say let x be the random variable, the outcome of a dice. The outcome of a dice. So there can be an outcome which is a 1, there can be an outcome which is a 2. So the probabilities of this respective outcome, the probability of you getting an outcome which is 1 is 1 out of 6. The probability of you getting an outcome which is a 2 is also 1 out of 6. The probability of you getting an outcome which is a 3 is also 1 out of 6. The probability of you getting an outcome which is a 4 is also 1 out of 6, because they are equally likely. As I've told you, a Ludo game, they are supposed to be uniform. That should be equally likely. That's what we call a fair die. So if these possibilities are equally likely, 5 is also 1 out of 6. And the possibility of x is equal 6 is equal 1 out of what? 6. So this random variable, our outcomes of a die, first is a discrete random variable. Discrete in the nature that is taking on whole numbers. 1, 2, 3, 4, 5, 6. Taking on these numbers. That's 1. Then 2 is a random variable, because when we sum these probabilities, we get 1. For all PDFs, the sums of probability should be equal to 1. So that means we can write our probability distribution as that x, and the probability of x is equal to x. So our 1 is possibility is 1 out of 6, getting a 2 is 1 out of 6, getting a 3 is 1 out of 6, getting a 4 is 1 out of 6, getting a 5 is 1 out of 6, getting a 6 is 1 out of 6. So the sums of all these probabilities of all of x, probability of x is equal to x, is equal to 1 out of 6 plus 1 out of 6 plus 1 out of 6 1 out of 6 plus 1 out of 6 plus 1 out of 6, and this 6 out of 6, and this is equal to 1. And it is a probability distribution which is discrete. It is a discrete probability distribution because it's taking on whole numbers, or it's taking on counting numbers. That's about a discrete probability distribution. Does not always stop on numbers. You can also have a discrete probability distribution for a coin. From our probability theory, from O level, we say a coin has got a head and a tail. We discussed that in O level. A coin is having a head and a tail. Now, and what's a head? Some people say that the head is the one which is having the head of something, like a head of a fish, but ideally a head is supposed to be having the coat of arms, the national emblem, then a tail is the other side. Now when you toss this coin, there are two possibilities from our probability theory of O level, which you must be having by now. When you toss this our coin, now when you toss this coin, this is our next example, by the way. This is our example 3. When you toss this coin, in the first toss you may get a head and a tail. This is what we discussed in probability theory. This is the first toss. Now in the first toss I may get a head or a tail. When I toss it the second time, I may still get a head or a tail. I may also, if I've got a tail, I may still get a head or a tail in the second toss. So when a coin is tossed From our probability theory, we're aware we're getting either first toss this, but we may be interested. Our random variable is the number of heads. The number of heads. Now, if our interest is the number of what? Heads. This is our random variable, number of what? Heads. So the question therefore is, how many heads we have? So that means what? We must generate the sample space first. In these two tosses, our sample space would be one, a head and a head. This is the first one. First toss a head, I may get a head and a head. The second, I may get a head and a tail. That's that. Suppose I've got first a tail. The second toss, I may get a head. I may get a tail and a tail. These are all from probability theory. As I told you earlier on, these are the basics which we borrow from our probability theory now. Now, the outcomes are, possible outcomes are a head and a head, a head and a tail and a head, a tail and a tail. But we need not change to write this with their respective probabilities. But when you observe the number of heads as our outcomes, this one is having two heads, this is having one head, this one head is not having any head. So that means our random variable x, the number of heads, is taking on values of 0 heads when we have all tails. It's taking only 1 when you have only one head, this one and this one. And it's taking on 2. So it's a random phenomenon. That's to begin with. The possibility that now you get 0 head, that means you have now the possibility of x being equal to 0. 0 head, that means the first one is a tail. The first one is a tail, and the second one is a tail. In such a scenario, what is this possibility? So it's the number of this over our sample space. So the number of this is just 1 out of 4. Then the next one, what would be now the possibility of having one head? In such a situation, having one head, that means what? We have the number of those values where we have one head, where we have a head and a tail, then a tail and a head, over the number of elements in the sample space, which is equal to, how many are they? These ones are 2. So 2 out of 4. Then the possibility of having 2 heads. This is only having a head first, then a head also second. So that means that's 1 out of 4. So in such a situation, we can therefore generate a probability distribution of the number of heads which appear when a coin has been tossed 2 times. And we said earlier on the probability theory that tossing a coin 2 times is the same as tossing one coin. Tossing a coin 2 times is the same as tossing 2 coins once. Keep that in your mind. I hope you remember that. So tossing this coin 2 times is the same as tossing 2 coins once. So we can therefore write this as a probability distribution of our coin when it's tossed. So you can say a probability distribution of the number of heads when a coin is tossed twice. So the number of heads when a coin is twice, this probability distribution shall be x, and the possibility of x is equal to x. So our probability distribution will be having 0, 1, and 2. So ideally, this possibility we have already said, having 0 is 1 out of 4. Having this is 2 out of 4. Having this is a quarter. And the sums of probabilities is equal to 1. So that's that. So with that one, now I want to move to the next part. The next part of generating a PDF. Now, generating a probability density function is as simple as one, looking at probabilities and their respective probabilities. Example, two dice are tossed ones. If a random variable is the sum of the outcome of the two dice. Now, our random variable is the sum of the outcome of the two dice. That means, from our probability theory, we shall have our two dice having the sample space. The first die 1, will be having 1, 2, 3, 4, 5, and you toss. Those are expected outcomes. Then we can also have die 2 having 1, 2, 3, 4, 5, and 6. Now, the sum, our interest is the sum of the outcomes. So if one die gives us 1 and the other one gives us 1, its sum will be 2. If the other one gives us 2 and the other gives us 1, its sum will be 3. If this one gives us 3 and this one gives us 1, its sum will be 4. Onwards, this will be 5, 6, and 7. Similarly, if the other one gives us a sum which is 1, then this one gives us 2, the sum will be 3. The sum here will be 4. The sum there will be 5. The sum there will be 6. The sum there will be 7 and 8. Now, when we sum, if this one die 1 gives us this and this one gives us, the sum will be 4. The sum here will be 5. The sum of this, if this one gives us 3 and this one 3, the sum here will be 6. So ideally, the sum here will be 7, 8, and 9. Now, you can also have sums which are 5, 6, 7, 8, 9, and 10. Sums which are 6, 7, 8, 9, 10, 11. So it continues. The sum of this is 7, 8, 9, 10, 11, and 12. So our outcome, the sum, the random variable is the sum. So these are sums. So, and you see these are discrete. By definition of a discrete random variable, these are discrete. They are taking on counting numbers. They are not taking on any decimals. So it is a discrete probability distribution. It is probability distribution, 1, because there's a chance of getting a 2, there's a chance of getting a 3, 2 3s, there's a chance of getting a 4s here. So it becomes a probability distribution. So we want to generate a probability density function for this. Now, the question therefore is, what do we do? Since our outcome is the sum, that means we must work out all probabilities of each outcome here. The probability of getting a 2, the probability of getting a 3, the probability of getting a 4, the probability of getting a 5, the probability of getting a 6, the probability of getting a 7, the probability of getting a 8, the probability of getting a 9, probability of getting a sum which is 10, and the probability of getting 11. Then lastly, the probability of getting a sum which is 12. Now, when you observe them, how many observations are those? More probability theory again. You can see, as an applied math student, we are keeping on referring back to our theories, which we did in O level. Now, so if The probability, the outcome is a 2, and we call it x1. So the probability of getting a sum which is a 2, because there's no 1, so there's no need of us writing that one. So our first sum is a 2. So how many 2's are there? There's only 1, 2. How many observations are there? These are 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So there are 36 sums. So the possibility of getting an observation which is a 2 is 1 out of 36. The possibility of getting an observation, if we were to write them all like this, second observation shall be equal to the possibility of getting a sum which is a 3. So how many are they? There are 2 3s, so that's a total of 36. Then we continue. The possibility of getting an observation, the third observation is a 4. So the probability of getting x is equal to a 4. A sum which is 4. How many 4's are here? 1, 2, 3. So that's 3 out of 36. The possibility of getting another sum, the fourth observation, the fourth sum, I'm calling them x and answer. So the probability of getting that one as a observation 5. Now what is this probability? How many 5's are here? 1, 2, 3, 4. So that's 4 out of 36. The possibility of getting another observation, which is x5. Probability of getting 6. How many are this? This is 1, 2, 3, 4, 5. So that's 5 out of 36. The possibility of getting another sum, which is called the probability of a sum, which is a 7. Next one is a 7. And it's good for you to write them in order so that you can be able to form a probability density function easily. When you write them in order, you can observe them carefully. So getting a 7, this is 1, 2, 3, 4, 5, 6. So this is 6 out of 36. Next one is the probability of getting an observation, which is equal to the probability of getting a sum which is 8. Probability of getting a sum which is 8 is 1, 2, 3, 4, 5. So this is 5 out of 36. The probability of getting a sum observation, which sum is, for this matter, is equal to 9. So how many 9's are here? 1, 2, 3, 4. So that's equal to 4 out of 36. So you proceed. The probability of getting another one, an observation, which is equal to probability, the next observation is 10. So our 10, how many 10's are here? 1, 2, 3. So that's 3 out of 36. And then second last, the probability of getting another observation, x10, which is equal to the probability of getting x is equal to observation which is 11, a sum which is 11. So these are 1, 2. So that's 2 out of 36. And lastly, the probability of getting the observation, a sum which is 12. So that is equal to 1 out of 36. Now, these are our respective probabilities. Now, with these respective probabilities, we can generate what we call a probability density function. A probability density function. Now, our probability density function will be this. Probability density function. A function that allocates probabilities. Probability density function. The function which is going to allocate our probabilities shall be the probability of x is equal to x. We should have defined our x as we said, the sum. Our x is the sum. The sum. Keep that in your mind. Our x is the sum. And the sums are 2, 3, 4, 5, 6, and their respective probabilities are this one. So we write a probabilities function in this format, right, like this, vertical bracket. That's how we write them. Then you must be observant and a little bit intelligent, just some small intelligence. Just observe the observations. Here there's no formula, but just some simple logic. You observe, because we want to get a link between this and its respective probability. You study this and its respective probability. So when you study them, you see that when I reduce this by 1, I get here 1. When I reduce by 1, I get here 2. When I reduce this by 1, I get here 3. When I reduce this one by that, I get there 4. So again, in the background, I can call this x minus 1. Because when I say 2 minus 1, then I put over 36 as a constant, because this one's 36. See? So I will have generated a function of observation. No need of looking for an equation here, because the probability may not be linear. It may not even be quadratic. It's a random phenomena. And since it's a random phenomena, it is by chance. And since by chance, it's just important for you to observe how they are occurring. Like you can work out the probability that somebody will die when he goes to a hospital, depending on the type of the hospital, depending on the readiness of the hospital to receive a COVID patient for the case of COVID. So ideally, that's that. But for which values are these satisfied? Satisfied for when x is equal to 2, when the sum is 2, when the sum is 3, when the sum is 4, satisfying here. When the sum is 5, it's okay. When it's 5, I subtract 1, I get that 4. When the sum is 6, it's also being satisfied. When the sum is 7, 7 minus 1, I get 36. When I try here, when it's 8 here, when it's 8, I subtract 1, it doesn't. So it's working up to 7. Working up to 7 here, like this. Now that means I must also now look at another pattern between this and this one for the remaining bits. Now when I study these observations, there's also something unique about them. This one and this one. This one and this one. I will still maintain my 36. Doesn't hurt me maintaining my 36 there. So when I study this and this, I add this and this, I get 13. 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 Therefore, I can say my next value shall be 13 minus x. Because when I say 13 minus 8, I get 5. So I will say over 36. That's the intelligence I'm talking about. You study how do you get this, that was the link between this and that. So the link is that 13 minus this, I get that 5. So I will say 13 minus 8 over 36. Then the next one will be 13 minus 9. 13 minus 9, I get 4. 13 minus 10, I get 3. 13 minus this, I get 2. So it takes on values, which one? For values 8, 9, 10, okay, you can flex some space here. For values for x is equal to 8, 9, 10, 11, and 12. This is a probability density function, and 0 otherwise. 0 otherwise. Sometimes we write 0 elsewhere. Now why do we write this 0 elsewhere? It means that anything outside these values, the probability is 0. The probability does not exist. Anything outside these values. For these sums, the probability outside these values is 0. So we write and say 0 otherwise or 0 elsewhere. Now this is what we call a probability density function. A function which allocates probabilities. And how does it allocate? Illustration. How does it allocate probabilities? This simple illustration. When, for example, I have this PDF, I will just say the probability of x is equal to 2 I substitute to the function from our beginning theory of functions. Where I get now x, I put 2. So I put here, that's 2 minus 1 over 36. I will get 1 out of 36. So it has allocated a probability of 2 when x is 2. I substitute in the formula there. It is allocated a probability because our probability. So I go the next one. Don't forget, still our probability of x is equal to x is equal to x minus 1 over 36. So when I allocate the probability of x is equal to, for example, 7, this will be equal to 7 minus 1 over 36, and this is equal to 6 out of 36. So it has allocated this value, its respective probability correctly. So it's called a probability-based function. It allocates these values, their respective probabilities. So it's a PDL. Similarly, I could also say the probability of x is equal to 12 shall be equal to 13 minus 12 over 36. This is equal to 1 out of 36. And I consider this one and I substitute there. So it's a PDL because it allocates the respective probabilities. So it's called a probability density function. Now, suppose you have been given this distribution. Given if you are given a distribution as simple as that for x, 0 elsewhere, 0 elsewhere, then somebody says find a, the value of x, the value of x, then the value of k, the value of k. B, the probability of x is bigger than 2. C, the probability of 1 is less than x is less than 3. Now in such a situation, if you are given this distribution, 1, you know that it's discrete. Why is it discrete? Because I've told you that it's taken on values in 1, 2, and 3. So it's a discrete random variable. It's a discrete random variable. Now, since this one is a discrete random variable, that means what? I can substitute these values there. I can substitute these respective values there. So that means I can say, therefore, or since it's the probability, the probability of x is equal to 1 shall be equal to k times 1, and I get there k. The probability of x is equal to 2 shall be equal to my k times 2, which is equal to 2k. The probability of x is equal to 3 shall be equal to k times 3, which is equal to 3k. Just substituting this because, be aware, our probability, which is discrete, is kx. So I'll just substitute where I get x, I put it as, so when x is equal to 1, I put that 1 there, I put in that function, and I substitute this into that. When x is 2, I substitute it into that value there, like that. So the respective probabilities now, for 1 its probability is k, for 2 is probability this one, for 3 is probability that one. So the value of k therefore is got by using our our concept which we said as a note. We said the sum of all of x, the probability of x is equal to x, should be equal to 1. That means what? This implies that when I add k plus 2k plus 3k, I get a 1. And here I get a 6k is equal to 1. Therefore, my k is equal to 1 out of 6. So, once you have got this, then now you can answer this other question and that other question, once you have got k. But if you don't have this in your mind, that means you cannot work it out. So, first, understand that for the probability distribution, its respective probabilities should be equal to, the sums of probability should be equal to 1. When you add their probabilities, you get 1, and then you simplify. Basically, that's that. Now, after getting that, we can now, as I've told you, you can now work out those probabilities after getting case 1 out of 6. That means what? You can now generate even a probability distribution. We have got our k to be 1 out of 6. That means the probability, our probability distribution will be like this. We shall have the probability of x is equal to x. When x, it takes on values 1, I take on counting numbers. So 1, 2, and 3. When x1 was said, the probability of x is equal to 1 shall be equal to k times 1, which is equal to k. So this is 1 out of what? 6. The probability of x is equal to 2 is equal to k times 2, which is equal to 2k. So this is 2 out of 6. The probability of x is equal to 3 shall be equal to k times 3, equal to 3k. So this is 3 out of 6, 3 times k. So once we have this, then we can work out anything they want us to work out. We can now come here and say, therefore, for the b part, the probability of x is bigger than 2. Now, the number which is the observation which is bigger than 2. So here, the observation which is bigger than 2 is only 3. So that means this is equal to the probability of x is equal to 3 alone. And this is equal to 3 out of 6. Basically, that's that. And this is equal to half. Then the next one, the C part, the probability that 1 is less than x, which is less than 3. Now, by idea, what's this? 1 is less than x, which is less than that. That means what? We are dealing with the only 2 also. That value which is equal to 2. It's less, 1 is less than x, that means x is bigger than you see, 1 is less than x, that means x is bigger than 1. So that means we are dealing with the 2. But it must also be less than 3, that means we are dealing with the 2. So the probability of x is equal to 2 shall be equal to 2 out of 6, and this is equal to so similarly, if I'm to add a bit, suppose they had asked me to work out the probability of 1 is less or equal to x, which is less than 3. So this one would be equal to, what are these values now? 1 is less or equal to x. That means I'm interested in x is equal to 1 plus x must be less than 3 plus x is equal to 2. I'm interested in those ones. So ideally this would be equal to, when this one is 1, that will be 1 out of 6. When x is 2, will be 2 out of 6. So you add that one, will be 3 out of 6. So this would be a probability. So basically, that's that. So, what have we done in this lesson? Before you do the exercise, it's important for you to understand what we have done and keep it in your mind. One, we have done, as a summary, we have done probability distributions. Now, we have defined a variable, anything which changes. We have defined a random variable, those ones which take on outcomes, which are random by nature, therefore they give what we call a probability distribution. And a probability distribution is just those outcomes, their respective probabilities. And I would say that this probability distribution are divided into two: discrete probability distributions and continuous probability distributions. Discrete probability distributions take on all numbers or counting numbers and sometimes negative integers. Then continuous probability distribution take on values in a given range, including decimals in that range. Continuous. Example of a continuous random variable is a normal distribution, which we shall look at a later stage. There are also others where we shall just be integrating, so we'll be revising that bit of integration. We have also done how to sketch, where we said when you are sketching, you draw a graph, which is the probability against observations. That's the basic sketch. You must have them as vertical lines. And then we have explained when you are given a probability distribution, you can generate a function, a probability density function. And that function is the one which allocates probabilities. If you can do that, then you should be able to run through this exercise, which is running from number 1 up to number 10. Certainly, for you as a student of principal math, you are not the other student who's going to do 1 or 2 numbers alone. You must practice. So run through these numbers from number 1 up to number 10. And then from there we shall move on to other concepts which we shall introduce next time. We shall handle the issue of the mean, the variance, the standard deviation, and other properties of discrete random variables. We shall look at that in detail next time. Properties of a discrete random variable, other properties of the expectation, properties of the variance, and how you work out them, and the mode. That's basically the end for this lesson. I wish you the very best. Right, Carlo?